could you reset it in 30 seconds? Or you another Wi-Fi problem? Yeah. Okay. Now we're about to get more people. Well, all right. So that's the second talk in the separation logic section. And now we are going to see how separation logic plays along with testing to give us symbolic execution framework for JavaScript. And Jose Fracoso Santos is the presenter.
Hello everyone, I'm Jose Fracoso Santos, and I'm going to talk to you about JaVerT 2.0. It is our new tool for JavaScript verification and compositional testing that I developed at Imperial College London with Philippa Gardner, Petr Maksimovic, and Gabriela Sampaio. We are all here, so please come and talk to us if you're interested. JaVerT 2.0 is the latest tool in a series of papers and tools that we developed at Imperial. In particular, last year in POPL 18, we presented JaVerT, the first separation logic-based verification tool for JavaScript. And in PPDP 18, we presented Cosette, a symbolic execution tool based on Rosette for symbolic testing of JavaScript programs. JaVerT unifies our work with JaVerT 2.0 unifies our work with JaVerT and Cosette. And how does it do so? Well, it does so via a new form of compositional symbolic execution for JavaScript that combines classical symbolic execution with compositional program reasoning based on separation logic. And we designed this new compositional symbolic execution for JISL, our intermediate language for JavaScript analysis and verification. And we did what do we do? Well, we do full verification, as in JaVerT. We do all program symbolic testing, as in Cosette. And we also do automatic compositional testing based on bi-abduction. So all these different types of analysis require a different level of input from the user, and we illustrate this in this diagram here on the right. So let's take a closer look at how JaVerT 2.0 works. Basically, JaVerT 2.0 receives as input a JavaScript program, and it first compiles it to JISL using our trusted compiler from JavaScript to JISL, JS to JISL. Then we give this JISL program to our compositional symbolic execution engine for JISL. And with that, as I said before, we can do full verification. So in full verification mode, the JavaScript program comes annotated with pre and post conditions for functions, loop invariants, and logical commands such as optional fold and unfold annotations. If the program is verified, JaVerT 2.0 will generate a proof trace. If it's not verified, it will try to generate a concrete trace that invalidates one spec to be verified. In all program symbolic testing mode, the user provides a series of unit tests with symbolic values and first-order assertions expressing the constraints on the inputs and on the expected outputs. If no assertion fails, the user has a bounded verification guarantee. It means that we have a verification guarantee up to the bound to which JaVerT 2.0 unfold loops. If an assertion fails, then the tool generates a concrete model that causes that assertion to fail. Finally, in automatic compositional testing, with JaVerT 2.0 does not require any type of input from the user, so other than the program. So what it does is that it will find a concrete trace that causes the input program to throw a JavaScript native error. If no such trace is found, the user again obtains a bounded guarantee that the program does not throw a JavaScript native error up to the bound to which JaVerT 2.0 unfold loops. And now let's see how this works in practice. And I will illustrate this with a simple example of an expression evaluator. And so on the left of the slide, you can see the code of this expression evaluator. And this is an expression evaluator for a simple expression language comprising literals, values, unary operators, and binary operators. And we have here the function eval_expr that evaluates the expression E in the store. And on the right, what is the expression E? Is an abstract syntax tree that actually represents the expression. And we see here on the right of the example, an example of such an abstract syntax tree. So this may seem a very simple example, but it already contains lots of JavaScript-specific features that are challenging for static analysis, such as extensible objects, dynamic property accesses, prototype-based inheritance, internal functions, implicit type coercions, and so on. Well, they are listed in the slide, at least some of them. And so now I will explain very succinctly how this interpreter works, because it will be useful later in the talk. And in particular, I will tell you about the variable case and the unary operator case. So in the variable case, we first recover the name of the variable. So we do e.name. E is the abstract syntax tree corresponding to the variable. So when we do e.name, we get the name of the variable. And then we recover the value associated with this variable in the store. So we do store.get e.name, and you get the value associated with the variable. So in the unary operator case, it's slightly more convoluted, but not much. What we do is that we recover the argument of the unary operator. This is e.arg, and then we evaluate that argument in the store. So we do eval_expr store e.arg. So we evaluate the argument in the store. And then we obtain the value to which that argument evaluates, and then we apply the unary operator to that value. We do eval_unop, which is the function that applies the unary operator. Nothing of this is surprising, and now we want to verify this example. So we have JaVerT 2.0 in verification mode. So in verification mode, as I said before, we require pre and post conditions, loop invariants, and now we do automatic folding and unfolding of user-defined inductive predicates. Whereas before, in the first version of JaVerT, we required explicit folding and unfolding annotations. So how do we specify that program? In order to specify that program, we need to define a predicate that relates the abstract syntax tree of the expression to be evaluated with the value to which it evaluates. To this end, we define this predicate x_val E bindings V. So we see it on the left. And what does it mean? It means that E is the abstract syntax tree of an expression that evaluates to the value V under the bindings. And to get a feeling of this, I will explain two cases, the variable case and the unary operator case, which incidentally are the cases that I explained for the interpreter. So in the variable case, we see that E points to an object with property type with value var, so the string var, and this tells us that E is the abstract syntax tree of a variable, and property name #x, and #x is a logical variable. So, and what does it tell us also? It tells us that #x is associated with V in bindings, so the expression E evaluates to V under the bindings. In the unary operator case, so it's the one below, we see that E points to an object with property type with value unop, property OP associated with the logical variable #op, and property arg associated with the logical variable #arg. We see that #arg points to the AS3 of an object that evaluates to #v under bindings, and we see that if we apply #op to this #v, we get V. So basically, what we are saying here, we are clearly stating that E evaluates to V. So using this predicate, x_val, we can very easily specify our eval_expr function. Basically, in the precondition, what are we saying? We are saying that E evaluates to a given value #v under bindings, and that store points to a key value map with contents bindings. And in the post condition, what are we saying? We are saying that eval_expr returns #v, so the value to which V evaluates, and the resource of the precondition is left unchanged. So we have evaluated JaVerT 2.0 in verification mode on a series of standard data structure libraries that we implemented in JavaScript ourselves, including binary search trees, linked and singly linked and doubly linked lists, key value maps, and others. And we obtained times that are comparable to those that we obtained for JaVerT, but despite the fact that we are now doing the automatic folding and unfolding of inductive predicates. So we saw in the previous example that x per val is in fact an inductive predicate, and we didn't see in the code any annotation, any folding or unfolding of that predicate. So the second use case for JaVerT 2.0 is whole program symbolic testing, and here the user writes symbolic tests, and JaVerT 2.0 tries to generate concrete examples that invalidate the assertions of those tests. Here, JaVerT 2.0 advances our previous work in Cassette in that its symbolic analysis is 95 times faster than that of Cassette. And this slide, this slide is showing is two examples of symbolic tests that we can write for the reference interpreter that we've seen before. Basically, we have a symbolic test that passes, the one above, and one that fails. And they might seem a little bit difficult to read, so let's see. So the first test, what it says is that it asserts that if we call the function eval_expr with an argument whose JavaScript type is not object, we get a user-defined error with message expr. And this test passes. It's fine. The second one, it asserts that if we call the function eval_expr with an argument whose JavaScript type is object and we get an error, it will also be one of the user-defined errors. So it will not be a JavaScript native error. This test fails. And why does it fail? Well, it fails because in JavaScript, null has type object. And the code of the expression evaluator is not properly guarding against this case. We see that when we do type of null, we obtain the string object, and then we do null.type. And this generates a native error, in particular a type error. So JaVerT 2.0 in all program symbolic testing mode catches this bug. So we have evaluated JaVerT 2.0 in a whole program symbolic testing mode on a library that we obtained from NPM called Buckets. So Buckets has more than, let me check, 1,000 lines of code and 60,000 lines, 60,000 downloads. And results show that JaVerT 2.0 symbolic analysis is scalable. And why is it scalable? Because, well, we are able to analyze 9 million GSL commands in approximately 90 seconds. Unlike the concrete test suite that came with Buckets.js, the symbolic test suite that we built using JaVerT 2.0 has 100% line coverage, and it achieves this with 60% fewer tests than the original concrete test suite that came with Buckets.js. Additionally, we found 2 bugs that were missed by the concrete test suite. So basically, the message is that JaVerT, the all program symbolic testing mode of JaVerT 2.0 is useful now. So the final mode of operation of JaVerT 2.0 is this automatic compositional testing. And in the automatic compositional testing mode, the programmer does not provide any additional annotation, so it just gives us the program. And JaVerT 2.0 will try to find a concrete execution that causes the throwing of a native JavaScript error. And how does it do that? Well, it uses bi-abduction to construct 2 sets of specs. Success specs, a set of success specs that describe the correct behavior of the program up to a given bound, and a set of bug specs that describe the conditions under which the given program throws a JavaScript native error. And if we apply this JaVerT 2.0 in automatic compositional testing mode to the expression evaluator that we saw in this talk, we get a bunch of success specs that describe the behavior of the reference interpreter up to a given bound, and we also obtain the bug spec corresponding to the bug that we've seen before, the null case. So we don't need to write a symbolic test to tell us that there will be a bug. JaVerT 2.0 will give us, look, if you give null to the interpreter, you will have the bug at this type error, so you're not properly guarding against this error. We have evaluated this aspect, the automatic compositional testing mode of JaVerT 2.0 in the data structure libraries implemented by us and on which we also evaluated the verification aspect. We believe that the times are encouraging, and we are now in the process of applying JaVerT 2.0 in fully automatic mode to the buckets library. We were already able to find one of the bugs that we found with the whole program symbolic testing for a simplified version of the library. The analysis is not yet fully scalable due to the internal branching of the JavaScript semantics, and we are working on this. So I'm now going to describe at a very high level the structure of our tool. So in particular, we implemented JaVerT 2.0 as a parametric module system in OCaml, consisting of 3 modules. The semantics module that receives as input a state instantiation and generates the appropriate version of the JSON semantics, a specification module that receives the state instantiation and extends it with support for separation logic assertions and separation logic summaries, and the bi-abductive module that receives as input a state instantiation and extends it with support for automatic inference of resource. So, illustrating this, so if we give to the semantics module a concrete state, we've recovered the concrete semantics of JSON. Analogously, if we give to the semantics module a symbolic state, we get a symbolic semantics of JSON. And we use this symbolic semantics to implement the whole program symbolic testing mode of JaVerT 2.0. Now, this is going to get more complicated, so it's good to look to the diagram on the right. So now what we do is that we pick the symbolic state and we put it inside the specification module. So, and then we obtain a symbolic state with support for separation logic predicates and summaries. And then we pick that state and we put it inside the semantics module. So we obtain a symbolic semantics with support for separation logic predicates and summaries. And we use this version of the semantics to implement our verification, the verification mode of the tool. Finally, and this is the biggest, it's like a matryoshka. So what we pick a symbolic state, we put it inside the specification module, obtaining a state with support for separation logic predicates and summaries. We pick that state and we put it inside the bi-abductive module, and so we also get support for automatic inference of resource. And then we put that inside the semantics module, and so we add the symbolic semantics with support for separation logic predicates and summaries and automatic inference of resource. And with this one, we construct our automatic compositional testing tool. So basically what I presented was JaVerT 2.0. It's our tool for JavaScript analysis and compositional testing. It supports verification, all program symbolic testing, and automatic compositional testing. It is built in this parametric way using this parametric module system. In future, we aim at generalizing it, our infrastructure, for arbitrary memory models instead of restricting ourselves to the JSON memory model. And our end goal is to build a general framework for streamlining the development of compositional symbolic execution tools based on separation logic. We also plan on building more modules, for instance, a module for describing event semantics on top of the JSON semantics and concolic symbolic executions. And basically, these are our plans for now. Thank you, and this concludes my talk.
All right. Let's go for the questions. The first one is anonymous from Slido. Why are you modeling the bindings as a set instead of a map? Does that mean that you allow variables to be associated with different values?
No, we could have modeled that as, in fact, this is a simplified version of the example. In the real example, we are using this joint union and being careful not to have overlapping like that in the definition of the bindings.
All right. Questions from the audience? All right. More questions from Slido. How reusable are your auxiliary predicates from slide 6? Are they program specific or more general than that?
From slide?
6.
So the ones on slide 6 are program specific, but we have a bunch of predicates for describing JavaScript internals and JavaScript standard data structures.
So does it mean that the client in an arbitrary case also needs to define something like that for verifying the program?
So a client of the expression evaluator.
Client of your framework.
So the client of the framework will have to, in the verification mode, will have to define his own predicates that fit their use, that fit their the particular program that they want to verify. So in whole program symbolic testing and in compositional automatic testing, they don't have to define anything because the tool does that for them. Because the goal is not full verification. In full verification, we need to provide, the predicates need to be provided.
All right. More questions from the audience? No. All right. Let's thank the speaker again. Okay. We have a couple of minutes to align with the